Hello everyone, this is Gautam Iyer and I'll be taking you through the second launchpad, that is F28069M based launchpad. I hope you have gone through the first part of the video, which was for the actual C2000 launchpad based off F28027. Now we are at the part 2, wherein I'll be covering the second launchpad, that is F28069M based. So F28069 based is again a controller based out of Piccolo series as F28027. So both of them belong to the Piccolo series, and F28029 is more powerful than F28027 when it comes to the performance. And also the most important part being F28069M has a floating point processor, so it's like it's faster in computations when compared to F28027. Also the clock frequency is 90 megahertz, if that compared to that of F28027, which runs at 60 megahertz. So let me just take you through the controller and the launchpad. So this is how the launchpad looks like. This is the F28069M launchpad, and as I previously mentioned that F and M basically they belong to the insta-spin paths. So M is for motion, as F was for FOC, field oriented control. M is for motion. So this 28069M belongs to the insta-spin motion part, especially meant for the motor control. So you can go through the literature. Over here you have the overview document, the user guide overview document. You have get started document. You have motorware for especially for your all motor solutions, libraries for motorware. And let me take you through the controller. Let us check the specs. The datasheet can be downloaded from the home page, revision F. And for F28069M, the best part being it has a technical reference manual and not different user guides for different peripherals. So you have one single document called technical reference manual. So this is the one, technical reference manual, and you have all the peripherals listed under one single manual. So that is the technical reference guide. So you'll have all the peripherals listed in one manual itself. So you can refer that for detailed peripheral analysis and study. Data sheet from here, and let me talk about the device specs. So this has an FPU, the most important, the processing accelerator. It has FPU, VCU, and DMA, so floating point unit, Viterbi coding unit, and dynamic memory access. So it has all three of them. It has something called as CLA, control accelerator, which is a coprocessor. So C28X is there for sure. On top of it, you have another parallel processor which can process few of the tasks. That is called CLA, and it is a parallel processor. So basically you have processors running parallelly with that of your C28X algos. So that's another plus point with 69, wherein it has a CLA. The MIPS is around 180 because it's like 90 meg of C28X and 90 meg of CLA. So both run at the same frequency, 90 megahertz. It has a 256 KB of flash, 100 KB of RAM, and again it's like with respect to the package, it has around 16 or 14 PWM channels, 8 HR PWMs, 3 caps, 2 to 1 E quadrature encoder pulse, it's like QEP modules, 16 or 12 ADC channels. The main difference being it has more communication peripherals, 2 SPIs, 2 UARTs, if compared to just one each of for F28027. And again, the plus point being it has 3 more connectivity features, that is USB, MEC BSP and CAN. So today in one of the demo sessions we'll be exploring CAN. So this is something which is more powerful than the F28002X family. So, and again it's like the pin package being 100 STQFP in which it's available, and so this info is available on the home page itself, so you can have a look here itself. Now let me take you through the user guide, that is the technical reference manual. So let me just take you through the manual, wherein you'll get an idea how the peripheral listing is being done over here itself. Yes, so here itself, table contents. So if you have a look here, you have your system control interrupts, you have your boot ROM, you have ePWM over here, HRPWM. So all the user guides that were in the form of different PDFs for F28002X family over here is listed in one single document. So it becomes very easy to just go through one document, and you can directly navigate to any of these peripherals from the bookmarks. So it becomes very easy. So it's like if you want to go through the ADC module, you can directly click on the ADC and you can have a look. So this is the mother document, especially to get all the knowledge about the peripherals, all the register base, and the data sheet as usual has all its brief info about what this controller is capable of, and all the pinouts, its muxing, and all the basic data. So that's about the data sheet. So these are the two important documents. As for the user guide for the Launchpad, you can download it from here itself. This is the overview. So you can directly download this. This will be having all the basic info about the Launchpad. So let me just download. I'll give you an overview. So you have a getting started, and all these Launchpads basically come with a demo code. So it's like it will give you an idea about what the demo application is all about and how you can observe the data of the demo application. Then it has all your header information, the other detailed Launchpad information. So like for example over here, as you can see, it has a 40-pin booster pack plug-in module connector, serial muxing jumpers, power jumpers, the controller itself, etc. So all the detailed info about the Launchpad, you can get it in this user guide, the Launchpad user guide, which is downloadable from the Launchpad homepage. So now let me take you through the design files for the Launchpad and the example codes for F28006X family or 69. As for the design files, you can navigate to TI Control Suite development kits, and you can find the Launchpad folder for 28069M, which is this one, and you have the Launchpad demo project over here itself. So the project that comes with the whole Launchpad is over here. You can go through the source code and the main hardware package, wherein you have the schematic, you have the PCB board and the artwork. So you can find it over here. So let us just quickly go through what this Launchpad consists of. So basically the controller is interfaced with LEDs. You have two LEDs. You have a nice CAN peripheral with a transceiver already on board, so you don't require an external transceiver. So that's the best part of CAN, wherein you can directly connect your CAN L and H signal to the board. And you have a QQEP connector. You have two booster packs you can connect, because you have two booster pack connectors. You have a USB to serial, as was in the case of F28027 Launchpad 2. So and this is the document which takes you through all the extra hardware that is put upon the Launchpad. So you can find the same over here in hardware dev package. So this is about the resource for the Launchpad, and let me show you where you can find the example codes. You can navigate to Control Suite, Device Support, F28069M family, the latest one. So you have over here, you have two versions, wherein one is the pure CCS code for C28X core, and you have something for CLA. So the way we code for CLA is different. So these are the examples for CLA based codes, and the main interfacing, you can go through these codes wherein you have C28X interfacing with CLA. So these are few of the CLA based codes that are with respect to the interface of both these processors. So, and you can find all the example codes in this directory. Also, TI has introduced a new software package for the resources for C2000. It's called C2000ware. So this is the first version. So even over here, if I'm not sure whether Control Suite is going to be phased out or not, but C2000ware is, you also find all these resources. So in C2000ware device support F28086, you can find all the examples over here for C28 and again CLA. So you can find all those examples that we saw over there. All those are present here, and these examples have been compiled using the latest C2000 compiler. So that is the main difference. And so this is something new, but basically Control Suite as of now has all your development board resources, which C2000ware doesn't have as of now. So this is more flexy, and you'll get more detailed info in Control Suite. But you can download both Control Suite and C2000ware, wherein just in case, if because one issue what I faced is like running the Control Suite codes on the latest CCS version 7 compiler. It gave me XDAIS error. It's one of the tool which is required for building the Control Suite examples, which is not there for CCS version 7. So for that I had to go with the C2000ware, wherein those examples built immediately in CCS version 7. So you just have to be a bit careful, wherein Control Suite examples don't build in CCS version 7. It gives you an XDAIS error. Either you can download the tool and then get rid of that error, or else you can use the C2000ware directly. So that's your call. So now let me take you through a CCS example. I'll be giving a demo on one of the CCS example as well as a Simulink example. So let's start with the CCS example first. It's an SCI Echoback. We did LED blinking for the previous Launchpad. So now I'll be covering the SCI Echoback example for this controller F28069M. So as for the Launchpad, the GPIO that has been connected to the USB to UART converter is GPIO 28 and 29. So that's exactly what I have configured over here, and also in the example it's been done in the same way. SCI RXDA is GPIO 28 and TXDA is GPIO 29. So the SCI GPIO initialization is done over here. Rest, it's like the most important over here is like the initialization of SCI itself. So as you might know, for serial communication, the stop bit, your parity, your care bits, all these things have to be set. So as for the demo, it's been set accordingly, and depending on your requirement you can modify them. The CCR register, you can go through the user guide for SCI, and that will give you detailed info and the breakout of the CCR register itself, wherein you can change the number of stop bits, the number of parity, etc. So all those can be taken care there. Secondly, it's like the most important part over here is setting the baud rate, which is over here. If you can see, there are two parts wherein it's set. It's SCI H baud and SCI L baud. So let me just explain how this is calculated so that it becomes easy for you to set any baud rate. Yes. So in technical reference manual, let's move to the SCI peripheral, and over here in SCI registers you have one for SCI baud rate set. It's called SCI BRR. So this is the one. So in SCI BRR we need to set the BRR. So this is the formula to get the value of BRR. So let me quickly help you out how we do that. So as you can see, this in the sample code it's written, it's 9600 baud is what they're trying to set, and 124 is what they're feeding into both of these registers. So let me just explain how that is done. This is the formula. So this is the formula. So in the code itself, you can see LSP clock divided by BRR plus 1 into 8 is what your baud rate is. So baud rate we already have. So LSP clock also we have, baud rate we have, and these are constants. So LSP clock value is given over here. It's 22.5 megahertz. The device frequency is 90 meg, and 22.5 is because LSP clock is sys clock, that is 90 megahertz, divided by 4 is what we have set in this example. BRR equals to LSP clock, that is 22.5 megahertz, 2.5 megahertz, and that is divided by the baud rate 9600 into 8, which gives you 292.9, that is 293, minus 1 is 292 again. So let us now convert this 292 to hex value. The decimal is 292 and the hex value we get is 124. So 124 is what we get BRR. So we load 1, most significant bit 1 to H, and 24 to your L. So this is how we get 124 for 9600 baud rate. So similarly for 115200 for other baud rates you can calculate. So this is how it's done. And now let me take you through the main code. You have two subroutines wherein where you're doing just a single transmit as well as a character or a string transmit in short. So all we do is we send in transmit we are sending an integer to the buff and we directly burst it. Over here we take it in an array and we keep bursting one by one. So this is all we do in these routines. As far for the code goes, it's like what basically we do is like once the initializations are done, what we do is we first print hello world, then we ask the user to enter a character. Once he enters a character, we display the same back again. That's done over here. So whatever I sent will be received in received character, and we display you sent the received character. So whatever I write, I get it back. So you'll get more idea when I give you a terminal demo. So what I'll do is I'll just burn this code. My launchpad is over here. Let me burn this code. And by the time this guy burns, let us go to the terminal app. Yes. So I'll just connect to the board. Let me press the play button. The moment I do that, now you can see, right? Hello world. You'll enter a character and the DSP will echo it back. So that's exactly what will happen. So enter a character, I'm entering G. So you immediately get you sent G. And if I write H, you sent H. So it's echoing back whatever you're writing. So this is what it does. So this is what the whole example program is all about. And this you can use it as a base to build up a serial communication for your project accordingly. I hope you were able to follow the CCS demo. Moving on to the Simulink demo, I've built a model wherein we can cover as much as peripherals as possible. Over here, as you can see, we have a PWM, we have a capture module, CAN and GPIO. So let me just explain what we're doing here. We are generating a PWM pulse. We'll be capturing this PWM pulse. We'll be calculating the frequency of that pulse and then transmitting through CAN. So this is what we're doing here. Over here, what we're doing, we're just blinking the LED. So just as we have a provision of 2 LEDs on the board, we are doing blinking. And we have one commented section wherein when, for example, if you have around, if your application demands for more PWMs than what the controller has, what you can do is you can use a capture module as PWM. So that is what this commented section is, using a capture module as a PWM generator. eCAP as a PWM will not have all the PWM features, as this is an enhanced PWM module, but you'll be able to generate a PWM model and control the duty as well. So that's about this. So let me go through the model block by block. So over here in ePWM model, what we are doing is, like, we are in this module we are simply just enabling PWM 1A channel, that is GPIO 00. We are giving a timer period for around 0.000, which means around 0.00072 divided by answer will give you around 1.388. So this is somewhere around 1.388 kilohertz or 1388 hertz. So this is what we are generating, and what I'm doing on the hardware is, in the launchpad, I'm shorting this PWM pin to the capture pin. So this is what I'm doing here. I'll show you how I do that. Let me switch on the camera. Yes, so I'm shorting in this way. As you can see, my violet wire is shorted to the green wire. So my violet wire is the PWM pulse and my green one is the capture pulse, capture input. So I'm shorting both of these, and rest, as for the duty, I've just kept 50% as the duty. So it's a 50% duty based PWM signal. Capture configuration, it's eCAP 1 on the board, and pass through with a sample time. So every 1 second I'm capturing this pulse and I'm generating the value. So these are the capture counts that I'll be generating. This is my converter. This will have a gain or an equation basically, which will convert these capture counts into the frequency. Okay, and this frequency in hertz is transmitted to CAN. So if we have a look at the converter, all we do is we do a reciprocal and then we multiply it with a gain. That is, gain is nothing but your processor speed, that is around 90 megahertz is what your processor is running at. So 90 megahertz is your multiplier, and you're dividing the counts, you're taking its reciprocal. So that's all we do in the converter section, and then we transmit it. So let me show you how this works. So let me open my CANmate. Let me first dump the code. So now that it's built, let us check what we get in the CANmate. Let us see the CAN data. So I'll do a start reception, and as you can see, every second we are getting a value of 560. So what is this 560? It's a hex value. So all we have to do is we have to convert this hex value, that is 560, into decimal, and we get 1376 hertz, and we set 1388 hertz. So now you can just imagine we are very nearby, and it depends on the capture also. So we basically have filters on the capture so that you can avoid these kind of noises and the deviations from the mean value. So what we read is around 1376. Now let us experiment for another value also. Let us change the PWM frequency to 2 kilohertz. So for 2 kilohertz it would be 0.005. 0005. So let me again build, and as you can see, it's like this would be basically real time, wherein you'll be having a control algo wherein you're continuously capturing your input frequency, for example your line frequency maybe 50 hertz or 60 hertz, and you keep your capture module will keep checking whether you're in the limit or not of 50 hertz. So you can hardly deviate from 49.6 to 50.4 maybe. So that would be your deviation limit, and you have to keep observing whether you are within that limit. So that's where your eCAP module it's very helpful. So now that this is built, now let's check what we get. So we are getting 7B6. So let us just check what the 7B6 is. In hex it's 7B6. In decimal it gives you 1974. So what we had set was 2 kilohertz, that is 2000 hertz. We get 1974 hertz. So you can just see, right, you have some amount of very small deviation, but you can you get the decent value. So that's what this is all about. And let me show you the LED blinking that is happening over here at the same time. So this is the LED blinking that is happening every 1 second. It's turning on and off, both the LEDs. So it's connected to GPIO 34 and GPIO 39. So let us go through the configuration, that is your model configurations. It's already open over here, yes. So as you can see, the hardware board is F28069 and the controller is F28069. The build action is build, load and run as usual. The only difference that I was able to find is like for the F28069 Simulink for MATLAB 2016B, what Simulink has as a debugger for F28069 is XDS100 version 1 and not version 2. So this target configuration file, you have to modify the current one, or else you can create a new one using CCS. So I did the later, wherein I created a new target configuration file using the CCS, and then I imported the same over here. So this one change you'll have to do. Apart from that, your CAN configuration of 1 megahertz of 1 Mbps speed is over here, and all your GPIO configs are over here, and it's equivalent to all your C28X controller. So the configuration is all same. You can modify according to your requirements. So this is the hardware configuration. So I hope you guys understood the whole model. Let me also quickly show you what is the difference. So this is the main difference, wherein in operating mode for eCAP, you either go for an eCAP or else for an ePWM. So asynchronous PWM is what this block is configured as, because we are configuring eCAP as PWM and not a capture. So when you do that, this menu will get activated. So when you are into eCAP, this menu will be activated, and when you are configuring eCAP as a PWM, this menu will be activated. And for ePWM, all you need is your period and your duty cycle. So this is what you have that basic info that you can feed, and then you can use your eCAP as a PWM. So I hope you guys understood how these blocks are configured. Thank you.